And the only probability model that we discussed on Monday was the binomial distribution. Okay? So here's the definition for the binomial model. So this is used when you have Bernoulli trials. And these trials are independent. And you know that this trial will result only two types of outcomes, a success and a failure. So when you have such type of random variable that only has two outcomes, then you know that you're dealing with a Bernoulli random variable. So the random variable, this Bernoulli random variable that equals the number of trials, the result in a success has a binomial random variable. And we can compute the probability of such random variable using the binomial distribution, which is here. It's this function right here. Okay? So we discussed a couple of applications. If you remember this example, we were trying to find out what is the probability of finding two pollutant samples on the next 18 samples. So something that I want you to start understanding is that the type of distribution that we're going to be using is directly related to the type of random variable that we are dealing with. Okay? So what I'm going to do today for each type of problem that we cover in class, I'm going to try to define a random variable so you can start relating the type of random variable with the probability distribution that we're going to be using. So for example, in this problem, the random variable can be defined as, let me use x. X will be the random variable, which is the number of trials that result in a success. So every time that you see such type of random variable, for example here we have find the probability that in the next 18 samples exactly 2 contain the pollutant, this type of random variable relates to the one that I just wrote at the top of the slide. It is the number of trials that result in a success. So for this problem, part A, we're looking at exactly 2. Every time that you see a problem with such type of random variable, then you know that you can use the binomial distribution to compute the probability. Okay, so if you can describe the random variable in such a way, like this one, random variable is the number of trials that result in a success, then you know that you're dealing with a Bernoulli trial, and you can use the binomial distribution to compute a probability. Okay? So this is for the first example. Then we cover how to compute the mean and the variance for the binomial. Here's the second example. And one more time, in this problem we have what is the probability, that's part A, what is the probability that for exactly 3 calls the lines are occupied. So in this first part of the problem, our success is to find a call or a line that is occupied. Okay? So again, we are looking at in this specific part of the problem, that number, the probability that that number equals 3. So we are looking at the number of times or the number of times to get 3 successes. Okay? So again, this random variable x can be described as this random variable as the number of trials that result in a success. And we are dealing with a binomial distribution to compute such a probability. Okay, so now that we understand the binomial, we can transition to a different type of distribution. And today we're going to start with the hypergeometric distribution. And again, this type of distribution is going to be applied to a different type of random variable. Okay? So we are finding the probability of specifically what is the probability of the result of this type of random variable. So before we get to the hypergeometric, I want to provide a comparison between the binomial and this new distribution. And the main difference is that the concept of replacements and independence. Okay? So for the binomial, we assume sampling with replacement, which means that you can take a sample and return it back to your population. But for the hypergeometric, our analysis is going to be based only on the sample that we get from the population. So the hypergeometric, so the binomial assumes independence, while the hypergeometric does not. So in the hypergeometric distribution, the probability associated with getting X successes in the sample. And you're going to see this more clearly on the next slide. So for the hypergeometric distribution, we start with a set of n objects. And very important that you notice that we're using capital N here. So we're going to have a big N to describe the number of objects that we have in our experiment. Okay? Then, from this group, there are k objects that are classified as successes. Okay, so from this big group, we have a number of objects that are classified as successes. And then the difference between the total and the number of successes, we have the objects that are classified as failures. Okay? Now, from this group, capital N, we are going to select or a sample of n objects randomly. So this n is going to be less than capital N. And this is going to be selected without replacement. And again, capital N is going to be less than or equal to n, so that sample could be equal to the size of the whole thing. Now, let the random variable x denote the number of successes in the sample. Then, x is a hypergeometric random variable that is described by this probability function. Okay, so remember from our discussion for the material of the first exam, there were a couple of problems that I asked you to solve, and I asked you to solve them based on the concept that we learned up to that point. But now I'm going to show you that those concepts are used to define the hypergeometric distribution. And it should be able to remember this type of expression for some of your problems. So specifically, let's look at this example. So in this problem, we have cars that arrive in dealerships in lots of 10. Okay, so our lots are of size 10. And 5 out of each 10 are inspected. So for each lot, we're going to inspect 5 of the cars. So for one lot, it is known that 2 out of 10 do not meet the prescribed safety standards. So the question is, what is the probability that at least 1 out of the 5 tested from that lot will be found not meeting safety standards? Okay, so again, we are looking at the number of successes. Here is at least 1 out of the 5. But again, we are not looking at the whole sample. We are looking only to the smallest sample that we get out of the 10. So in this case, we are looking only at 5 out of the 10, which are the ones that are going to be expected. So if we want to define again a random variable for this type of problem, x is a random variable which is described as the number of successes from a sample. Sorry, you have a question? You? Okay. Okay. From a sample n obtained from a larger sample that is described by capital N. Okay, so every time you see a random variable that is described based on this definition of a random variable, then you know that you can compute the probability using the probability, the hypergeometric distribution. Okay, so this example follows the hypergeometric because a random variable of size n is selected without replacement from n items. So you have a group of 10 and you're selecting only 5 to be expected. Second, k of n items may be classified as successes and n minus k are failures. So in this case, it's very clear that we know that 2 out of 10 do not meet the prescribed safety standards. And then the probability associated with getting x successes is that in the sample is given that there's k successes in the log. So based on this description of the problem, then we can figure out that this follows a hypergeometric distribution. Okay, so what I would recommend you to do from now on is every time we describe a distribution, write the type of random variable that we are trying to address with that type of distribution. Okay, so this is a hypergeometric, and once you see that description at the top, you're going to start noticing the differences between the problems and also between the random variables. So let's try to solve these problems. So in our example, we have k, which is equal to the number of successes, and this is equal to 2. Remember, 2 out of the 10 are the ones that are defective. Okay? We have an n, capital N, which is the size of the log, which equals 10. And we know that we're only looking at a smaller sample to do the testing. Okay? So, in this case, the size of that sample is 5. Are we clear up to there? So we have 10, we are only looking at 5 of them, and we know that 2 of them are defective. And x will be the number found, which will be equal to 1 or 2. So we're looking at the probability of x being greater or equal to x, and that will be equal to the probability of x equals 1 plus the probability of x equals 2. We only have 2 defective items in this log. If we solve that, the only thing that you have to do is to substitute the distribution or the parameters into the distribution. So going back to the expression, k, again, is the number of successes. X is the probability that you're looking at, or the outcome. We're going to have 1 and 2. N is the size, or capital N is the size of the log. K, again, is the same as here. N is the size of the sample, of the smaller sample, which is 5, minus x, which is the outcome that you're looking at that point. And you know how to solve this expression, right? We describe that this, for this case, will be equal to k factorial times k factorial n minus x factorial. Right? So, for each expression, you're going to have to solve this. So for this problem, we have the expression for x equals 1 and the expression for x equals 2. And when solving that, we get a probability of 778, which means that that probability is almost 78%. So how do you feel about that probability? Can you give me a feedback based on that number, based on the experiment that you're trying to address? 78% is a high probability. Again, the question is, what is the probability that at least one out of the 5 tested from that lot will be found not meeting the standards? So that probability is almost 80%. So your testing, even though it's based on only 5 units, will be kind of accurate with high probability. Okay? You know that if you increase the size of your sample, you get to 10, then you're going to have a probability of 100%, right? If you decrease the sample, the chances are that you're going to have a lower probability. The more units you study or analyze, the better your probability of finding a defective component or auto model. Does that make sense? So from now on, I'm going to also try to find out if you understand what's the meaning of that probability. Okay, so let's transition to the next. We can also compute the mean and the variance for this type of distribution, and I'm not going to go through the derivation of such an expression, but here we have the mean or the expected value for the hypergeometric random variable, which equals n times k divided by the capital N, and we also have the expression for the variance. So if I ask you what are the expected number of calls or cars that fail inspection in our example, what will be your answer? And again, this relates to the problem that we discussed on Monday. I'm asking again about the expected value. Here, using a different word, what is the expected number? Every time you see expected, that word, or the mean, you know that we're trying to find out what is the mean or the expectation of such random variable. So the expected number of cars that fail inspection in this example is going to be given by this mean, because this is a hypergeometric random variable. So if you solve this, oops, I'll cut down here. If you solve this, mu is going to be equal to n times k divided by n. So here we have the size of the sample is 5 times the number of successes is 2. Then this divided by the size of the total that we are analyzing. So this is going to be equal to 1. So the expected number of cars that will fail inspection is going to be, or the mean value will be 1. You can compute the standard deviation using this expression right here. And as you can see, it's a very big, large expression. You gotta be careful when you're computing the variance for the hypergeometric. So the variance will be equal to 5 over 9 times 5 times 2 over 10 times 1 minus 2 over 10. And this is 4.444. Are we done? Problem is asking for the standard deviation. So you have to take the square root of this, and that's equal to 0.667. Okay, so I'm going to give you 5 minutes to look at the next problem. Try to solve it on your own. Or at least state the probabilities for A and B. So what I mean is state the expression for A. Slow markers. So for A, let me know what goes in here, and B, what goes in here. And you gotta, yes. Sure. Okay. This is based again on the problem. So we know that 2 out of 10 do not meet the prescribed safety standards. So we are categorizing those automobiles that do not satisfy these standards as our successes. Okay, so we know from data that out of the 10, 2 of them are the ones that are not passing the standards. So those are classified as our successes. Good question. Any other question? So again, the first thing that you need to do is to define what is your random variable. So that will be the number of cars in the sample that are defective. So this is going back to the definition of a random variable. If you define the random variable in such a way, then you can identify what type of distribution you can use to compute the probability. Okay? So in this case, you have the number of cars in the sample. You have a small sample. You have your 140 cars, and you're only selecting 20 of them to compute the probability. So your smaller sample is going to be equal to 20. Okay, this is also telling you that you have you're selecting or you're sampling without replacement. That's one of the characteristics of the hypergeometric, so that's also size 5. And the first question is asking if 20 cars are defective, what is the probability that at least one defective car is in the sample? So how would you state that probability for part A? Is this the probability of, we know that X is our random variable because we define X as the number of cars in the sample that are defective. If you look at this problem, you see a keyword here will be this, at least. So when you see at least, you know that you're looking to a lower bound. You need to define that lower bound, and you know that you're looking at the probability of that lower bound and above. So that's what at least means. Okay? So here we're looking at the probability of X being greater or equal to 1. Does that make sense? Okay, again, this is very important. This is very important. You need to define this. Be able to define those probabilities. If you define that wrong, your problem is going to be wrong. You're going to be computing a wrong probability. So, again, very important point, how to define that. Now, we are looking at the sample of 20 cars. Are you going to find the probability for 1, 2, 3, 4, 5, up to 20? Of course not. You can look at the complement, right? So this is going to be the same as computing this probability, 1 minus the probability of X being equal to 0. So if you look at the complement, then you only have to compute the probability for X equals 0. Okay, so for this case, we have the probability of X being equal to 0. is equal to, what I'm going to do is just substitute the values or the parameters into the hypergeometric distribution, because I know this problem satisfies the conditions for a hypergeometric, so I can use the hypergeometric to compute that probability. And again, this is based on the random variable. How you define the random variable based on the problem? So we define the random variable, and we know that this problem satisfies the condition for a hypergeometric. So we can use the hypergeometric. So I'm going to substitute those values here. We have 20, 0. You have 140 minus 20. 20 minus 0 divided by 140, 20. If you solve this, if you have a calculator capable of solving all these together, I have a TI-89. I can plug in these numbers and it's going to give me the solution right away, but I don't know what type of calculator you have. For the purpose of the exam, if you cannot compute this, I'll allow you to state this and this. Okay? That's going to tell me that you know how to compute that probability, even though you don't have the capability on your hands in terms of time. Okay? So this is equal to 0.0356. So again, if you look at this probability, this is around 4%. So that probability is very low. So if 20 cars are defective, if you're only selecting 20 from the 140, the probabilities of you finding a defective car is very small. So if you want to find a defective car, you might need to increase your sample. Instead of selecting 20, you might raise that to 70, 80. That should increase your probability. Yes, sir.
Wouldn't that one be the, or wouldn't the 20 be the complement, actually? Wouldn't we flip?
Oh, yeah. Yeah, you're right. I apologize for that. What we computed is just a probability of x being equal to 0, and that is correct. So we are looking at the complement of that. So the actual probability is going to be equal to 1 minus the probability of x being equal to 0, and that is 1 minus 0.0356, which equals, this is a probability of x being greater or equal to 1, so this is going to be equal to 0.9644. Okay, so based on that number, this is almost 96%. So my conclusion now is different. This is about 96%. So the chances of you finding a defective car based only on the sample of 20 is very high. It's almost 96%. Okay, so that's what we can conclude about this first part. Now, what is the part B saying is, if 5 cars are defective, what is the probability that at least one defective car appears in the sample? So our sample is about the same. The only difference is now that we only have 5 cars that are defective. So the probability is still the same. Which is going to be the probability of x of 1 minus the probability of x equals 0. The only difference now is when you compute this, instead of 20 you have 5, 0 times 140 minus 5, 20 minus 0 divided by 140 and 20. and that equals this, and we are looking at the complement. 1 minus 0.4571. So that probability is 0.5429. Okay, so the only difference now is that the number of defective units went from 20 to 5. But you see now, since now the number of defectives is smaller, the probability, which was 96% when you had 20 defectives, went down to 54%. Does that make sense? Does make sense. No? Why not? So what we're saying is we have a large group of units, let's say 100, 140, and we are selecting 20 out of that group. Okay, so we have 20 here, but we know beforehand for part A that out of the 140, 20 are defective. So from this batch, 20 are defective, we're selecting 20, and we are trying to find out what is the probability of finding one defective from that group. So since you have 20 defective out of the 140, you have higher probability of selecting defective units from your sample. But now if you decrease to 5, then that means that out of the 140 parts, only 5 are defective. You're still picking 20 as your sample, but since you have a lower number of defectives, your probability of finding a defective is going to be way smaller. Okay? Is that clear? Okay. So again, understanding these numbers is also important. Okay, so the last thing for this part of the lecture, or for this distribution, is to understand that you can also approximate the hypergeometric with the binomial distribution. And that only applies when n is way bigger than the sample that you select. So you have 1,000 and you're selecting 5, for example. Then we can approximate the hypergeometric using the binomial distribution, and this is an example. So we have automobiles arriving into a data shifting lots of 100, and 5 out of each 100 are inspected. The probability of 0.2 are the ones that are below the safety standards. So what is the probability that at least 1 out of that 5 inspected will not meet the standards? So based on the example, we know that we can compute that probability using this expression. But if you use the hypergeometric, then you can state that using where 0 is x is 0, number of defectives is 5, and n equals 20. So you can compute that probability using the hypergeometric, using those parameters. And you can also get the same probability by stating that as a binomial. So remember, for binomial, we also use x equals 0, and n equals 5, p equals 0.2. So there are some cases in which you can use a binomial to approximate the hypergeometric. Okay? So now we're going to transition to a different type of distribution, which is called the negative binomial. And I can tell you that you're going to have a lab based on this distribution today. So it will be good for you to pay attention and understand what we are explaining. So let's go to the next set of slides, and this is lecture 9. We are looking at the probability distributions again, but we are looking at a new group of distributions. Specifically, we're going to look at the negative binomial and the geometric, and also to the Poisson distribution. These are the same learning objectives for this lecture. Let's go straight to the negative binomial. So binomial experiment is in which trials are repeated until a fixed number of successes occur is a negative binomial distribution or a negative binomial random variable. So again, we are looking at the specific number of trials that are repeated until a specific number of successes is found. Okay, so for example, study code data indicates that 30% of all bits transmitted through a digital transmission channel are received in error. An engineer is running an experiment to try to classify these errors, and we'll start by gathering data on the first 10 errors and count. So we're going to look at this sample, and we want to find what is the probability that the 10th error will occur on the 25th trial. So again, we want to find out what is the probability of finding X number of successes in a specific number of trials. That's the negative binomial distribution. So we can define okay, so this example follows the negative binomial distribution. Again, we have repeated independent trials. The probability of success is equals to P, and the probability of failure will be 1 minus P, which is the complement of the probability. Again, we want to understand what is the random variable that we are using. So for the negative binomial, we use X, which is the number of trials on which case is the success occurs. So the probability associated with the case success in occurring on trial X will be given by this expression. So this expression is kind of similar to the binomial distribution, but now we're going to have some differences here. And again, you need to be aware of the type of random variable that you are looking at for the experiment. Okay, so for this expression we have K, which is the success number. X is the trial on which that K success occurs. P is the probability of success. And Q equals 1 minus P, which is 1 minus the probability of success. We also have some formulas to compute the mean and the variance for the binomial random variables. So the mean is computed by dividing the number or the success number by the probability of success, and the variance is given by the K success number times 1 minus the probability of success divided by the probability of success squared. So we have the information that we need for the negative binomial. Let's find out how to apply it. So on the next example, actually this is the same example, I just want to give you the solution. So for our example is K equals the success number of success is 10. Again, the question is what is the probability that the 10th error will occur on the 25th trial? So the success number is 10. The trial number on which K needs to occur is 25. The probability of success is 0.3, and the difference is 1 minus P. So putting those parameters into the negative binomial function, we can obtain the probability which equals 0.037, which is about 4%. So the probability of finding this is about 4%. So that probability that having the 10 error occurring on the 25th trial is very small. We have another example here. A website contains 3 identical computer servers. Only one is used to operate the site, and the other 2 are spares that can be activated in the case the primary system fails. The probability of a failure in the primary computer or any activated spare system equals, from a request for service, is 0.0005, very small. Assuming that each request represents an independent trial, what is the mean number of requests until failure of all 3 servers? Okay, so I'm going to give you an idea. This is a negative binomial distribution. Okay? And we can find out one by defining the random variable. So this is x. It's a random variable of number of trials until on which the k success occurred. But the question is asking for something different. Question is asking, what is the mean number of requests? So there's a keyword there. It's the mean number. What are we looking at? Expected value. Mean, the expected value, average, all refers to the same thing. We're looking at the expected value. And we now have to compute the expected value for a negative binomial. It's right here. So the expected value, or mu, is going to be equal to, so we know the probability of failure. (0.0005), and we know the mean number. What is the mean number? Equals the expectation, which is the expected value of x. And for the negative binomial, we know that the expected value of x is going to be equal to mu, which equals k divided by p, where k is the number of successes. Sir, if I see you texting again in the classroom, I'm going to ask you to leave the classroom. Okay, this is the second time. Okay, so for this case, mu will be equal to 3 divided by 0.0005, and this is 6,000 requests. So, for this problem, the number or the average number of requests until a failure of 3 servers, of all of them, is going to be around 6,000 requests. Okay, so you need to go through all those requests until you can see that event of seeing all the servers failing. Okay, now I have another question for you here. This is, what is the probability that all three servers fail within 5 requests. Anyone like to try to express that for this random variable in terms of the probability? And I'll give that person a point for the next exam. You want to try it here. If I can find a marker. So what is the probability that all three servers fail within 3 requests? So look at the definition of the random variable. Random variable is the number of trials until in which the key success occur. And the question is asking what is the probability that all 3 servers fail within 3 requests. Okay, so we can state that probability with x being less than or equal to 5. You want to know that it will require at least 5 requests. So at least it's less than or equal. No, I'm sorry. What is the probability that all 3 servers fail within 5 requests? So at most 5 requests. Okay, within 0 and 5. So that probability is being x less than or equal to 5. What happened? Can you have the probability being equal to, if you're looking at the 3 servers, what would be the probability of x being equal to 2? Can you have all 3 servers failing after 2 requests? No, because you're going to need at least 3, right, to make them fail. 1 per server. Okay, so the probability of x being equal to 0 or the probability of x being less than or equal to 2 will be equal to 0 for this problem. Because if you want them to fail, all of them, we have 3 servers, you're going to need at least 1 request for each server. So this becomes, therefore, the probability of x being less than or equal to 5 will be equal to the probability of x equals 3 plus the probability of x equal 4 plus the probability of x equal 5. So you know that all of them can fail if you have 3 requests, all of them can fail if you have 4 requests, all of them can fail if you have 5 requests. 5 is the top provided by the question. So if you solve this, then let me write the expression for you. So this is 3 minus 1, 3 minus 1, 0.0005, 0.9995, 3 minus 3, plus 4 minus 1, 3 minus 1, 0.0005, 0.9995, 4 minus 3, plus 5 minus 1, 3 minus 1, 0.0005, 3 times 0.9995, 5 minus 3. And that, once you solve that, this is equal to 1.249 times t 10 to the minus 9. So that probability is very small. It's almost 0. Or very close to 0. It's 0.00000001 something. Okay? So the chances or the probability of having all of them failing within 5 requests is very small. It's almost 0. Okay, so you will need more than 5. And the expected value actually is telling you that on average you're going to need 6,000 for them to fail, all of them to fail. So by just looking at 5, you know that the chances are very small, which is what the question is telling you, or the result is telling you. Okay? So, yes.
I don't understand the what is the probability that all three how that shifts. X is less than 5. But there's two variables you're talking about.
Well, the random variable is what we define as X, and it is the number of trials that you would need until achieving a number of successes, right? So that's your random variable, that is X. So you can need 10 trials, you can need 20 trials, you can need 100 trials, that's your random variable. And that's what we're saying as our probability. Now the other part that you're mentioning is not a variable, it is the number of successes that you will require. So in this case, in order to, the question is asking all of the servers to fail. So your success will be having all of them, 3 of them fail. So the question basically is, how many tries will you need to achieve this number of successes? In this case, the number of successes is defined by the number of servers that are going to fail. So in this case, we are looking at all of them, which are all of them, 3 of them. Okay, so again, for a negative binomial, the random variable is defined as the number of trials that you're going to need to achieve a certain number of successes. In this particular problem, the successes are the number of servers that are failing. So if we're looking at all of them, then the number of successes that you need to achieve is 3. Okay? And you're trying to find out what is the probability of achieving that number of successes with only 5 requests. And what the problem is telling you is with only 5 requests, the probability is going to be very small. Now, if you compute that same probability by increasing that 5 requests, let's say to 100, it's going to be very time consuming to compute, but you'll see that that probability will be very high. Well, higher than this. Okay? Does that answer your question? So again, we're looking at 2 different things. For the negative binomial, the random variable is defined as the number of trials that you're going to need to achieve a certain number of successes. So you need to find out what is in the problem, what is classified as success in your problem, and then use that to compute the probability. So I don't know if the problem makes this clear. Only one is to operate somewhere. Yeah, I think the problem is it doesn't state it clearly, but from the problem itself, we can find out based on the probability that the number of failures will be, or the service to fail, will be the success. Because the probability is defined, the probability of a failure in the primary computer from a request for service is 0.0005. Okay, so we can talk more about it if you still have doubts after the lecture. But again, for the negative binomial, you need to identify what will be classified as a success. And then again, the random variable is going to give you the probability of the number of trials that you're going to need to achieve that number of successes. Now, maybe with this example, we can have a better understanding of the negative binomial. So again, let me write that here. X is the number of trials until the kth number or successes occur. So here we have in a clinical study, volunteers are tested for a gene that has been found to increase the risk of a disease. The probability that a person carries the gene is 0.1, it's 10%. The first part of the question is asking what is the probability that 4 or more people will have to be tested before 2 with the gene are detected. So in this problem, what would be classified as a success? Exactly, it's finding a person who has the gene. That will be classified as a success. And what you're trying to find out is how many trials you will need to find this number of persons with that gene. Okay, so first part is what is the probability that 4 or more people would have to be tested before 2 with the gene are detected. So again, X is our random variable. It's the number of trials until the kth success occurred. So for A, what is the probability that we are looking at? Again, the probability is defined as based on the random variable. Our random variable is X. So that's correct. So X, it is the probability of X being greater or equal to 4. Because it's 4 or more people will have the gene, or needs to be tested in order to find 2 with the gene. Okay, so the probability of X being greater or equal to 4. Again, once you see this, you see that finding the complement will be easier. So X less than or equal to 4, which is going to be equal to 1 minus the probability of X equals 2 plus the probability of X equals 3. Why are we not computing 0 and 1? Correct. Probability of X being equal to 0 and X equal 1 will be 0 because you need at least 2 people to find such a probability. So it's not like X of 0 and X1 does not exist. Those probabilities are going to be 0 because you need at least 2 to find the number of successes that you require. Okay, so maybe I can put that here so I will not confuse you. So 0, 1, probability of X equals 2, and the probability of X equals 3. But we know these two are 0. Because you need at least 2 to satisfy that condition. So this will be equal to 1 minus, you're going to use the negative binomial, 2 minus 1, 2 minus 1, 0.1 squared times 1 minus 0.1, 2 minus 2, plus 3 minus 1, 2 minus 1, times 0.1 squared, 1 minus 0.1, 3 minus 2. And this is 1 minus 0.01 plus 0.080, which equals 0.972. This is about 97%. So, after identifying the type of distribution that you need, first thing I will do is to find the type of random variable that we're dealing with. Then, once I identify that random variable, I need to know what type of distribution can I use to solve the probability. Here, I'm giving you the type of random variable every time we solve a problem, so you can start identifying what we're dealing with. Okay, so the random variable is always defined in terms of x. The probability is going to be defined in terms of the random variable. Okay, so now, once we identify the type of distribution, you need to know what are the parameters. So in this case, you know what are the number of trials, you know what are the number of successes that you're trying to find out. So using those parameters, you can find the probability by just plugging in the parameters into the distribution that you're going to use. Okay, but the problem here is how to identify the distribution. So there's where you need to spend more time. Understanding the problem and finding out what the random variable is and what the problem is asking you. Once you get to this part, everything else is just plugging in the numbers. Okay? But getting this portion is the difficult part. Okay. Part B, how many people are expected to be tested before 2 with the gene are detected? There's a keyword there. See if you can identify it. Expected. Okay, so you have expected. You're dealing with the expected, the mean. What is the mean for this random variable? So how would you compute that? Correct. So the expectation for this random variable is k over p. P is 0.01. K is the number of successes, so this will be equal to 20. Where k is the number, k is the success number. Oh, okay. So it should be 0.1, sorry. Thank you. Thank you. Okay, so we have a couple of distributions that we need to discuss before get to the lab. So I will just stop here today. And again, so far we have discussed the binomial distribution, the negative binomial, and the hypergeometric distribution. Only 3. You need to make sure that you understand what those 3 distributions are asking for and how to use them, how to state the problems. This is going to get more complicated. I want you to do well on this part of the course because I know this material is very important. So you need to understand this. If not, you're going to have a lot of trouble later on your courses. So if you're able, if you want to get something from this class, it's this. Okay, because most of the time when you go to the industry, they're not going to tell you, okay, the arrival process of these parts follows an exponential distribution, so you can plug in that into your model. That's not how it works. And if you want to create a good model for your system and you want to be able to make good decisions, you need to go understand the process and see how you can estimate that distribution. So in the class, we've been showing you how to create a histogram. We can also show you, we've been also showing you how to create a distribution based on the histogram. And I'm going to show you also in this course how to pick a distribution based on the histogram. But again, you need to understand what the distributions are doing because most of the models that you're going to use to make future decisions are going to be using probability models for prediction purposes. So I will make an effort to show you more applied problems in the class Again, I'm going to show you a simulation model this time, but again, this material is very important. This is going to get more complicated again, because we're going to deal with continuous probability distribution later in the class. Okay, so I'll see you on Monday. Yes.
You type your questions on your test that we could get them back.
Yes. I have your text.